So I have started the recording. So now what I was trying to say that we will discuss the row vibration spectra first, and then the assignment 3 we will discuss, and then we will quickly finish for today. Next day we will go to the week 4, what I earlier thought that I would teach you. I saw that some parts are missing, some derivations are missing from sir's part regarding the row vibrational spectra and what really delta J plus 1 means and delta J minus 1 means. Someone may miss that what sir is trying to say. In a rotational spectra, we know delta J plus 1 means from J0 to J1 or J1 to J2, and delta J minus 1 means 1 to 0, 2 to 1 means the reverse, you can say like a relaxation process. But what does they really mean in row vibrational spectrum? Means when vibration and rotations are involved together. So did you understand what really delta J means, plus 1 means, and delta J minus 1 means?
Yes, I was able to understand.
Okay, so that's good. Then let us quickly do that, and we will quickly finish the week 3 assignment problems, and then we'll wrap it up. I think today will be done within 1 hour or 1 hour 15 minutes. So let me share my screen. Can you see my screen right now? The presentation?
Yes. Yes.
So these are the things all know, and electromagnetic spectrum. Today we will discuss mainly in this infrared region. Okay, so this is the part for vibrational spectra. Okay, now let me write down the basic things for vibrational spectra. As you know, so we will not write those things. We will quickly go to the row vibrational spectra, what Sarah has already mentioned. Other things I think you have already understood. So you tell me when you have some doubt or something like that. First case, when born Oppenheimer approximation holds. Okay. So this born Oppenheimer approximation holds means, let me draw the things what I am trying to discuss. This is a vibrational, so harmonic oscillator, you can, the parabola you can assume, and this is my first vibronic level. Okay, so this is my V equals to 0, and this is my, so what does actually do for rotational spectra with J is equal to 0? So what actually you observe that the energy spacing increase, right? So here it will look like it is same, but let me give you the main notation. When we use the double prime, that means the ground state. Okay, and when we use a notation only prime, that is actually the excited state, fast excited state. So this is actually true for vibronic level also. So if suppose V is equal to 0, this is actually V double dash. Okay, and this is V dash. So what I was trying to say, this is 0 equals to 0, 0 to 2, 3. Actually Sir has taken the opposite convention, but this is the general convention you will see in Banoel's book also. Okay. So can you hear me? Is my audio is clear right now?
Yes.
Okay.
Yes. Yes.
Okay. So row vibrational spectrum means, suppose we will consider transition from here to here. So suppose, so let me write down what is the general energy formula. So let me write down here. General energy formula E for a vibronic level J that will be nu bar vibration V plus, this is actually V plus half, right? We are going to write it in centimeter inverse. Okay, so this is the new bar wavelength. huh? We already divided it by HC, and for the rotational part we already know in centimeter inverse it is B into J plus 1 into centimeter inverse. So we are all taking it in centimeter inverse. So I am going to write it here. So epsilon V equals to 0, suppose. Okay. So V equals to 0 J prime. So what would it look like? 0 plus half, V is equal to 0, so it will be, so this part is actually easy, so this part we can do it quickly. And B for this is J prime plus 1, this is in centimeter inverse, and B equals to 1 part, this is J, this is not J double prime, this should be J prime, single one, J prime, that is V equals to now 1, so it will be 3 by 2 u bar vibration plus B. So one part I haven't discussed, that is, sir already mentioned that when the bond of approximation, Oppenheimer approximation hold, then for B is same for both, B is same, right, for both the vibronic levels. That is why we can take this, and the energy difference here it is in centimeter inverse, so that is equivalent to the wave number. So the what is the wave number of that transition is actually epsilon V equals to 1 J prime minus epsilon V equals to 0 J double prime. That will give you nu bar vibration plus V into now that will give you B into J prime square plus J prime minus J double prime square plus J double prime. Okay, so this is all in centimeter inverse, so I will write that at the end. So I am just showing you the steps of that derivation, how we have arrived there. J plus J minus, for this minus this part we can write it like that, right? 1 plus J prime plus J double prime, and this, and what is left, J prime plus, acha, so this is also minus, I am making a mistake, this is also J prime minus J double prime. So eventually what we are going to get, B, this is taking J prime minus J double prime, J prime plus J double prime plus 1, right? 1 will come from here, right? And these all in centimeter inverse. Now we have two situations for this. One, delta J is 1. So delta J 1 means delta J 1 means J prime means your this state is actually J double prime plus 1. Okay, that means the transition, suppose J prime to, sorry, okay, that means J prime to 1 for this. This is 1. 0 to 1. 1 to 2. Then 2 to 3. Okay, so this is the transition what we are talking about right now, that is delta J is plus 1. So how it will look, the wave number for the transition, that is, and new vibration would be as it is, plus b. Now j minus j prime will be 1, so j minus j prime is 1. I will not write anything, let me write 1. This is multiple, and j prime, and we can write it in terms of j prime, right? So j prime is already j double prime plus 1, so I will just write it once, so that, and j double prime is 1, so this is what I have written, and this part is already there. So eventually it becomes a new vibration bar plus 2b. So 2 will come out from this, j prime plus 1 centimeter inverse. Centimeter inverse is all over this, and for this transition j prime is 0, 1, 2, 3, anything. See, if j prime is 0, means for delta j equals to 1, if j prime is 0, so you won't have anything transition to j is equal to 0, right? J prime is equal to 0. You don't have anything j prime is equal to minus 1. So that you also have to understand. Now, when you have delta j equals to minus 1, that means we will take the different thing. Now, we will consider that from j prime is equal to 1, we will go to j prime is the 1 to j prime. Suppose what I am trying to say. So now the j prime is j double prime minus 1. You understand what I am trying to say? So suppose your j prime is now 1, it will go to j is equal to 0. So that means delta j is equal to minus 1. So that time what your wave number will look like. So new vibration, and so now you have understood that we will going to write it all in terms of j prime, not j double prime. So j minus j double prime would be minus 1. So instead of 1 we will write minus 1. And what will be here? We are replacing the things here. So j prime, in terms of j prime, what we can write? So that means j double prime is equal to j prime plus 1, right? So j prime plus j prime plus 1 plus 1. That eventually means new vibrational minus 2b j prime plus 1 centimeter inverse. Now here your j prime can grow from, as you can see, 0, 1, 2, 3, whatever. But your j double prime can't be 0. As you can see, if your j prime is 0, then your j double prime should start from 1, right? That I think you have right now understood. So for what is actually you got for delta j plus minus 1, you got new bar is equal to new vibrational plus minus 2b. Now I am writing j into j plus 1. Did you get this? No, I think I have made one mistake. Z won't be there, right? Yes. Did you get it? How to get it for this? I think this part is easy, right? So if I draw here, so now to come to 1, we will come from 2. So j prime is, if 1, j prime is now, if you 1, then your j double prime is 2, and if your now if you come from j equals j double prime 3, you will go to j double prime is equal to j prime is equal to 2. So this is what is delta j equals to minus 1. So can you tell me which is known as, so how would it look like? Means, just let me give you an idea. So as sir has already shown, so energy spectra is, suppose this is intensity, and this is suppose wave number, centimeter equal. So suppose this is your new vibrational. So this is also known as. So can you tell me what this new bar vibrational also known as? So what you got? What the expression was? Can you tell me what this new vibrational also known as? So do you expect? Yes, Avantika?
Yes, sorry.
So what this new bar vibrational also known as? Do you know what does it called?
Q branch?
What? What?
Q branch?
I really don't get got what you are saying, but I will give you one expression. You know, that is band center. Do you know anything band center?
Q branch.
Q, no, that is a different thing. P and acha, you are saying this is the Q branch, the PQR. Okay.
Yes.
Okay. So yeah, it could happen. So one thing also known as this is the band center. But do you expect that any intensity coming from this? Means do you expect for any molecule, suppose HCl or suppose HCN, do you expect anything to come from, not HCN, I should not write HCN, so then it will be a triatomic or polyatomic molecule. Right now we are discussing diatomic molecules, so HBr. So do you expect for any of these molecules, if you have a high resolution and instrument, so, and high resolution spectra, do you have any, what do you think? Is there will be any possibility of any intensity at a new vibrational, new bar vibrational?
No.
Why not? You are correct, but why not?
Because it also needs V. This is only new now. We also need V for
Yes,
this.
yes. So J can be from 0, 1, 2, 3, anything, right? Now, even if the J is 0, you will get 2B terms, right? Multiple of 2B terms will be there. The plus and minus thing will depend. If delta J is equal to plus 1, you will get plus 2B. If delta J is equal to minus, then there will be minus 2. So you will get something like what you already shown. Just center, around the band center, you will get something like this. I am trying to keep the spacing similar. And here also. This will be something symmetric, but ideally should have been expected. But anyway, you will know that that will not be ideal. So the main gap from here to here would be 4B, right? 4B centimeter inverse. So this is all in centimeter inverse we are talking. Suppose this is the increasing way. So this part is delta J equals to plus 1, right? And delta J equals to minus 1 for this. So this is known as which branch? P branch. I forgot actually.
Q.
No, delta J equals
Q.
to minus 1.
Oh, yeah, this one is P branch.
P branch. And delta J equals to plus 1, I think it is R branch, right?
R branch.
Yes. Now, so you know that there is also something called O and S branch. Do you know that? Is there
No.
is there something O and S? O P Q R S, right? And this side should be O P Q R S. So what I am trying to say, okay. So I will go step by step. So let me go to the next page. So now we will discuss the part. Where is my cursor? So now we will discuss the second part where the breakdown of bond Oppenheimer approximation. So the thing is same. What I'm trying to say now, the problem is for nu equals to 0, the B is B0, the nu equals to 1, B is B1. Why do you think, what do you think about why this is the case? Means, what does Bornheimer breakdown of Born-Oppenheimer approximation means? Before starting,
Uh, Von Oppenheimer approximation, it just means that we will take, different components of the system, first calculate one and then calculate the other one.
so that too we have
And
done. That too we have done for this
yeah,
also.
yeah, and this one is the opposite.
No,
What
here we have
that's what.
done we have took the separate thing, right? So what you are saying, I am just repeating. You said that for Born-Oppenheimer approximation, we can take these two parts separately. Are you saying that?
But I mean to say that we can take B same for all of this, and then we can calculate it. But for that, we have to take B different for each one.
Means why we have to take different events? Means means more physical answer I am trying. I am expecting. Means suppose what does Born-Oppenheimer approximation tells you that the two time scales are different. Okay, the two time for different vibrational energy scales or rotational energy scale do not interact with each other. So we can take them. We can say that that doesn't interact with each other. So we can take separately. Now, when the Born-Oppenheimer approximation will be breakdown means the vibrational energy levels and the rotational energy levels will interact. Means it is not so. What actually the case means? Ideal case is they won't interact, but in real they should interact, right? Because vibronic energy levels holds the rotational energy levels, right? And beyond that, electronic energy levels holds the vibronic levels. You know this, right? So when does the Oppenheimer approximation won't be hold? So they are trying to say that now the rotational energy levels will interact with the vibranic energy levels, and B won't be same. Understand? So you got that point. I got it that you will take different rotational constant for different vibronic levels. But the actual thing is now why we are taking that now, because the vibronic energy levels and rotational energy levels are now interacting. Okay. So now let us write the thing as per the previous thing. B equals to 0 and J prime. What we expect? We expect nu vibrational plus B0 J double prime plus 1 centimeter inverse, and E equals to 1 J double prime J single prime bar vibrational plus B1 now the difference would be epsilon, not epsilon, equals to 0 j double prime, that is, acha, am I making any mistake? Yes, I am making any mistake. You tell me. This is new bar vibration plus b1 j prime square plus j prime minus b0 j prime square plus j double prime. So I wanted to show this means I wanted to show you this derivation, how you could get this, because at Van Hoel also it was not the expression was given, but how the expression they are reaching, that is not there. So I'll try to solve for it. So I think you have already understood how that will come, or you understand the derivation, but for others also who will see this video on YouTube, maybe I will quickly do this. So you can tell me, right? So if you have solved it, you can tell me that now, for suppose we are going to take delta j equals to plus 1. So Avantika, please help me in this. So what should I write? So new bar. So that means j u prime is j double prime plus 1, right? Now how to solve this, or how to derive an equation from this, whatever the equation sir has mentioned. So did you derive that yourself?
Yeah, actually, I did.
Can you so we can do that together, right here? So tell me, this would be a good means exercise. So can you tell me what are the things should I take? Let me add.
We will
Yes.
we'll put the values of j prime first.
Oh, okay. So I'll just write it once in like this. So you want me to write the all the terms to j double prime, right? That's what you are saying?
Yes.
Okay, so let me do that. Vibration plus b1 j double prime is j double prime plus 1, that square. Right? Have I made any mistake? Actually, I will erase a few now. Then we'll start this. I have actually done mistake. Not mistake. On this it will be even lengthier. I have already done the derivation here also, but paper, so that I myself will fumble. So J prime, not J prime, but J prime, not J double prime. So this is J prime plus 1 minus 0 J double prime plus 1. Okay, so we'll take everything to J double prime. So J prime is J double prime plus 1. So here it would be J double prime plus 2 minus V naught. All the things will be in terms of uh, J prime, J double prime. Now what we can do, we can take the J double prime plus 1 common. So if we take common, what we will get? B1 J double prime plus 2 minus B0 J double prime. Okay, good. Now what we can do from here, new calculation up, plus J double prime plus 1. We can take B1 minus B0. That term, take by taking the J prime common, we also have 2B1, right, and nothing. So we will do one thing, we will take 1B0 and plus B0. That eventually means nothing, right? So to get a symmetrical thing, we will do that. J double prime plus 1. Now what we will get? B1 minus B0. It may, so you may have done this using a simpler thing. Okay, so don't worry. You may have done it much better way than me, but I could get this thing up to B1 and multiply by 1, and we have 1 B1 left plus B0. So did you get this part? Do you have any confusion till that part? Are you following that part?
Yes.
Let me know if I am making any mistake, because I am very prone to make mistakes. A double prime plus 1, and we can take B1 minus B0 common, and it would be J double prime plus 1, huh? Yes, and B1 plus B0. Now you can see you are getting back this thing, right? Mu vibration, or what Sarah has already shown, that 1 will be B1 plus B0 term, right, with J double prime plus 1, and another is B1 minus B0, but here we have J double prime plus 1 whole square. So J prime whole square, this part is there, and this is nothing. So what when the Born-Oppenheimer approximation holds, then that time you got nu bar is equal to nu v plus 2b, okay, and J double prime plus 1, something like that. So actually these B1 or B0 are not that much difference. What do you expect, that which one is bigger, B0 or B1? What is B? B is rotational constant, that is, can you tell me what is B? H by, I forgot, H by 4 pi square or 8 pi square, 8. I actually forgot. Do you remember? Can you tell me what is B?
A minute, just a minute. Also the
Yes.
B is H by 8 pi square mu R naught mu R squared by C. Sorry, C into C.
Okay, so I think I am correct, right? I have marked maybe. So don't mark up. So it will be given in, I think, but maybe B won't be given. B is, I think B is going to be very common. Just remember how to come to that from maybe the solution, or don't mark up. That would be good. So what do you think that which, if B0 is higher or B1 is high, means value of B0 or B1, what do you think? So as I have written the expression, so that does mean something, means you will get the hint from
B1
that.
should be higher.
B1 should be,
Higher.
B1 should be higher. Why that? Why is that? Why is that?
It's B1 minus B0, so I guess it should be positive, so B1 should be higher.
No, why do you think B1 minus B0 have to be positive? From the expression of mu bar, it could be negative also. So it doesn't really matter because other positive terms are already there, na? So what will
Yeah.
happen? So suppose you are in ground vibronic level, so that is your B0. Okay. Okay. So suppose this is your B0 for R0. Okay. And your B1 suppose is H. By all the other things are same, 8 pi square C. These things won't change, right? I is mu R square, right? I think rewriting it twice. So I don't have to write mu R1 square. So do you agree that only the whatever terms are there, only the most probable thing that can change is the length? Maybe in excited state the length is what do you expect? The bond distance should increase or decrease? And V is equal to
In
what?
excited,
Hmm?
in excited state.
Yes, excited vibronic, means fast excited vibronic level compared to the ground vibronic level.
It should increase,
It
I
should in,
guess.
it should increase. Means R1 should be bigger than R0, right?
Yes.
So then what will happen to then what will happen to the values of B1 and B0? Which one is higher and which one is lower?
B1 should be higher and B0 should be lower.
Okay, I am writing it again. I think B0 by B1, right? If I write it like that, so we already have for B0 we have 1 by R0 naught square. All the other terms are common, that it 1, and it is R1 square by 1. So now you tell me which is bigger, B0 or B1? So this is what, if you divide B0 by B1, so the first term is 1 by R naught square and the second term is divided by 1 by R naught square. That is actually, you can multiply it with R1 square, right? So is it greater than 1 or less than 1?
R1,
Hmm? I can't hear you. That is actually greater than 1, right? That is actually greater than 1. So your B0 is actually greater than the B1. So this is what also we have got for the isotopic effect, right? Yesterday,
yes.
that if you have some isotope, then the higher, where the mu is higher, then the rotational constant would get lower. Here also, if your bond
Yeah.
length would get high, means in these cases when the B1 and there is a difference B0 and B1, so b0 is actually greater than b1. So no matter what is going to be the j or whatever is the constant, this part is always going to be a negative thing, because j prime plus 1 whole square is always a positive number, and b1 minus b0 is always going to give you something negative. So this is going to be always negative. You can read it in Banuel's. Okay, so it is also given, and there is an important phenomena that means the gap between the observed spectra are going to change. So that I would suggest you to read from that. If you have any doubt, then I will help. Huh? So please check Banuel book for this case. And we need another A. Na? This is only A. So we will solve for delta j equals to minus 1 as well. Okay. So we will quickly do that. So what I am trying to do actually, that see, you have learned almost all the things in the lectures, in the videos. So I will try to add something to each of the lectures, so that and guide you to read what part from the book, so it would be helpful. Okay. So this is just and how to solve the sample questions. So we will just do that to enhance the learning material or the reading material. So nothing else. Huh? So professor is anyway there to teach you. I will just help you. So delta j negative now means similar things. The j prime is actually j double prime. What am I writing? J double prime minus 1 or plus 1? Minus 1, right? Am I writing it correctly? Yes. So
Yes.
new bar is what we already got, that new vibrational plus b1 j prime plus 1 minus b0 j double prime plus 1. So always remember, this is all in centimeter inverse, not per meter. So in mathematical problem, you could have been given a problem and you are expected to give some bond distance or something like that in meter inverse. So please remember that one. So anyway, so for delta j equals to negative, so what we can expect, new bar vibrational plus b1. Now we'll go to should I go to j prime? J prime is j double prime is j prime plus 1. So we will not change this part. Okay. So we will try to do a similar thing what we have done for the earlier one. J prime plus 2, right? So I am not writing the centimeter inverse. I will not write for the next part. So why I am saying you this unit thing a lot of time, because see, my specialization or whatever I wrote, maximum thing was physical chemistry, and I used to make mistakes in numerical problems in units, and that would be for your NET exam or GATE exam. They will play with the units. Means, see, you already know the formula and other things. So how can, so they will try to reduce your marks, right? So how they can do that? They will play a trick with the units. So always be careful and learn common relationship. You know, force is I will come to that in a numerical problem that is there in the week 3. So let us first do this. So what are we getting here? So we can take the j prime plus 1 common, right? We have b1 j prime minus b naught j prime plus 2. I will again J prime, and am I making any mistake? No. So if I take the J prime common, I will get B1 minus B0 right here, and left with minus 2B naught. Okay, I will not do step jump. Suppose I wrote J prime plus 1, now J prime B1 minus B0. Now suppose I am writing plus B1 minus B0. We already have, and I have to means again take a minus B1, so that B1 plus B1 minus B1 is 0, and I am left with one more B0. Same thing what we have done in the earlier case. So we will take, so this is C, B1 minus B0 is there, multiply by 1 suppose. So we will take common B1 minus B0, and here will be J prime plus 1, and if I take minus here, then it would be B1 plus B0, right? So again what we are going to get, that this I will take a minus, let me erase this part. So this is minus B1 plus B0, right? J prime plus 1 and plus B1 minus B0, J prime plus 1 also. So for delta G plus minus 1, here you get, for the both the cases I am writing together, new bar B vibration up plus minus B1 plus B0. Same thing, right? There was plus minus 2B, here you are getting B1 plus B0, and you already know this is the negative part you are going to get, right, in both the cases. So can you in both the cases that is plus. So you try to read what is the effect of that negative part here from the Banwell's book, as I have already told you, and you already knew that B1 is less than B0. So what do you expect, that how much, so what is the actual difference? Is it too much, or it would be very less? The difference, what do you expect? Means is it B1 less than B0, or B1 very less than, what I should say, means almost, so I should not write very less than, so that is actually means difference. What do you expect, that if it is almost close to B0, which one do you expect?
So not much difference. I mean, it will be less, but not that
Yes,
much.
this is right. So it's not equal, but the difference is very less. Actually, yes. So that's why this B1 plus B0 actually is very close to your 2B thing. Okay. So that's one part. So what you got from, so this is when Born Oppenheimer approximation breakdown, and when Braun Open approximation holds, in that time new bar was new vibration plus minus 2B J into J plus 1, suppose, or not this, buzzer is there, so I am using it too much. Anyway, so this is the thing what I am trying to say. All this in centimeter inverse. Okay. So now you got the derivation of that paj. I think sir has asked you to do the derivation yourself for the negative delta g equals to negative. I hope you have done that, and I am just showing you that thing. Okay. So this was the derivation part. I said that I will help you to solve. I think you yourself have done this part, right?
Sorry?
You yourself have did you derive this part yourself? This
Minus one?
minus one, yes.
No, I hadn't.
Okay, okay. So you get an idea, right? How you will do that, and how you are going to cover. And please read Banwell's book. This part, I forgot the page number. Just read this row vibrational spectra and this part, and what is the effect to the spectra. Huh? What will happen to the line width and other things. What will happen to the line width, not really line width, or what will be the happen to the gaps. Let me write it. Line width is width of one line. I am asking that what would be the gap between two lines, how it is going to change. Okay, means gap between two spectra. So I hope this part is clear. So we will try to solve the week 3 assignments quickly, and we'll leave it there. Huh? Or we can discuss a few perturbation part, so that you can solve the assignment. Right? The assignment I think is due tonight. So what do you think? What is the wave function of a harmonic oscillator will be?
Real?
Okay, so yeah, not much thing to discuss here. Yes, it will be a real. And for a harmonic oscillator, what do you think is true for out of all these options? The second question, for a harmonic oscillator, the lowest possible energy is 0. Is it true?
No.
So what is what it is called? 0 point energy, right? The lowest possible energy, or for V equals to 0, and that is half nu vibration or nu bar vibration. So that is actually non-zero. So this is second one is correct. And what about the rest of the two? Only the lowest energy level is usually unoccupied at room temperature, and higher energy levels can usually be occupied at room temperature. What do you think about this?
Only lowest energy level is occupied.
At the room temperature. Yes, and this does come from the Boltzmann distribution. And is there a role of degeneracy here? Means suppose for the rotational spectroscopy, the population depended on two things. One is degeneracy, that is 2j plus 1, because your angular momentum had 3 directions, right? And that depends on m values. We discussed it, right? And what about this vibrational thing? Will there be any factor like degeneracy comes to this population?
No, there's no degeneracy.
Yes,
I haven't
here
got.
there will be no degeneracy. So coming back to an earlier thing you had discussed, you asked me that what will the role of AM and L in rigid rotor. So in hydrogen atom, what? So I think I fumbled there. So I will write it here. AM will give you the orientation along the space. Orientation along the space. M or small L or something like that. Okay, along the space. So what will give you the for different quantum numbers? Now the suppose this is P or L. That is your angular momentum. So let me write it L only. So I'll erase this part. So the L will give you, or the big L will give you the shape of the orbital, or the shape. Here the shape, you will get the shape, and n in case of the hydrogen atom will give you the energy levels, right? Energy. So these are all what is one quantum number gives you. So in non-rigid, in a rigid rotor, m also will give you the orientation, that where the orbital, where the orbital angular momentum orientation of that, and L will give you the shape. So let us come back to the questions, and the third question is selection rule for harmonic oscillator arise from what? Is it arise from?
Hermite polynomial.
Yes. And where did you read Legendre polynomial? Can you remember?
Rigid rotor.
Was it
Rigid.
Legendre? Yes. And that is referred to the theta part, right, in hydrogen atom. And what are the polynomial? So did you read quantum mechanics?
Yes.
So you can ask, hydrogen atom you have read, right? So which polynomial do you use to in solution of the radial part of a hydrogen atom? Is it Laguerre?
Yes.
Yes. So remember. So you don't have to really remember the polynomials. Just name you can remember. Legendre for theta part, Laguerre for r part. Okay. So that is okay. And what about the third and fourth option? Are they spacing between the successive level of the oscillator? Does it really alter the selection rule, or does it really comes? Selection rule will come from selection
No.
transition moment.
I think requirement of non-zero transition moment is equal.
Yes, it would be required. Why it would be required? So if the transition moment integral is 0, then there is no transition, right? So that you need a non-zero transition moment integral. Okay. Now let us go to the question number 4. Very easy. Spacing between the successive energy levels of a harmonic oscillator. Does it
Same.
is same? And what about the rotational? What about a rigid rotor? What
It
about?
increases.
Is it really true? Yes. It increases. Yes. So I was just thinking about the 2B, that is the rotation means gap between the no, that is actually what is 2B? The spacing, right? Spacing between the spectral lines. So that is different. So it will increase 0 to B, 4B. So these are the energy levels, right? Am I making any mistakes? J plus 1. J plus 1, right? Yes. And for 3 it would be, I am making a mistake. Now it would be for 3 it would be 12B. So the gap is 6B, 4B. So they all have equal. This is 2B authors. Okay. So I will just doing a calculation for my own. I think you understood what I am trying to say. Anyway, so question number 5. For IR activity, it is essential that the molecule should have a dipole moment, or it may not have a
The
dipole.
dipole moment is YYB. Third one.
Yes. So this is coming because I think in selection rule there was a term du mu by dx, right? At x is equal to 0. That should not be 0. Then the overall transition moment integral would have been 0, right? So from there you understand that we change in the vibration, or due to vibration there will be a change in dipole moment. Then only we will get a transition moment integral, and then we will get a vibrational spectra. And what about the Raman spectroscopy? That has not yet been discussed, but I think Sir has told one line, right? For hydrogen or chlorine, how do we get the bond strength or something like that? Do you know?
I don't remember right now.
Actually, from Raman spectra, you will get the bond strength from molecules where there would not be any change in the suppose for some molecule where d mu by dx is equal to 0, or they may not have any permanent dipole moment. So for that molecule, that won't be IR active, but that would be a Raman active molecule. I think you have read somewhere maybe that the molecule which is Raman active may not be is not a IR active, but IR active is not a Raman active, something like that, vice versa, or inverse thing, reciprocal things, that is they are related. And from Raman spectroscopy you can get the bond strength for those molecules which doesn't have a dipole moment, or there won't be any change in the dipole moment. Okay, so that would be discussed later. But for question number 6, the spacing between the successive energy levels of an enharmonic oscillator, means now here comes the enharmonicity constant, right? The Xe and other things. What do you think? Let us write. So what is the energy? What would be the energy for a enharmonic oscillator? It would be V plus half EV plus mu bar vibrational plus plus or minus? What do you think? Minus, right?
Minus.
Yes, mu bar, so square of that. And what are the terms there? I forgot. New vibrational Xe, and new vibrational was there.
Yes.
Square of that, or only new vibration?
No, only new vibration.
Okay. So when this term will come, so what do we expect? That the spacing between successive energy levels of an enharmonic oscillator, what will happen? These are all
Decrease.
decrease, right? Yes, you are correct. Decrease with increase in energy. So you remember, right? These round shape options are MCQ, and the squares one are MSQ. So you remember that. And I think in assignment you will get partial marks. Suppose you have only selected the recursion formula from Hermite polynomial, and you did not select anything from the suppose non-zero transition meter, a non-zero transition moment integral. You have selected only one correct option, then you would have got the half the marks. Or suppose there are 3 options correct, then you have 1/3 of that marks. But if you have chose 2 correct options and a wrong option, suppose the second or the fourth one, then you would not have got any marks. Okay, just remember that. So choose during the solution of assignment, you can be careful. Suppose you have chose all the 2 correct answers, but then you choose a wrong answer, you would have got 0 there. And marks don't matter even anyway, because the end same will be there, or the final exam will be there. Anyway, so for question number 7, so did you get the correct answer for this? The 0 point.
Actually, no,
You didn't?
I got the wrong.
So did you get the same order, the 10 to the power minus 21 joule, or were you getting something different?
I was actually making mistake in the units. So
Yes. So let me open the calculator. Okay. So calculate it. So the 0 point energy is how much? The 0 point energy is E0. So EB is equal to 0, or this is, let me write it E. It is in joules, right? E is equal to capital E is half H new vibration. Nu is the frequency right now. I am not putting any bar. And new vibration frequency is also related via 1 by 2 pi over k by mu. What is k? K is force constant, right? And unit is given, that is Newton per meter. And how else you could have got the unit? You know force is kx or minus kx, or plus kx. I forgot.
minus.
Minus. Anyway, so force unit is Newton, you know, and x is meter, you know. So the unit for k would be Newton per meter. That you know. And what is Newton? Can you? So force is also mass into acceleration. Yeah. That means Newton is, if I take all the SI units, kg meter second minus 2, second to the power minus 2. So force constant is actually kg meter gone, second minus 2 is there. You understand what I am trying to do? So your mu is in kg, should be in SI unit, then this should be in kg second to the power minus 2, and it would be in kg. Then overall your A will be in second minus 2 under the roots, and eventually when it comes out it will be second minus 1, that is hertz, right? That is your frequency. So I am just letting you know that we have to take the reduced mass mu in kg, okay, to get the frequency in hertz, or to match the units. You understand what I am trying to say here?
Yeah.
Okay. So what is the reduced mass for 35 Cl2? That would be 35 into 35 by what? 35 plus 35, that is 70. That is AMU or gram per mole. Okay. Am I right?
No.
Okay.
Yes.
So what is it actually? So it is 17.5. So 35, this is 2, this is 17.5 gram per mole. So what this is in grams? So this is for a per mole, means for 6 per moles means 1 moles mean there are 6.023 into 10 to the power 23 molecules, right? Eight. Okay, so 7.5 gram per mole. Now so sorry, I was talking to my senior in the research matter. Okay, so where I was, so 1 mole means there are 6.023 into 10 to the power 23 number of molecules, not moles. Okay, so here we are discussing about only one of the molecule, right? So you have to take 17.5 by 6.023 into 10 to the power 23 gram per, now this is mole, okay, and it would be gram per molecule or per molecule, this is the weight. And you know this actually gives you 17.5 into, so I am just breaking it down into some form so that it could feel similar, minus 24 grams, okay, and in kg it would have been 17.5, 1.66 into 10 to the power minus 27, right? Did you follow this part, what I am doing, Avantika?
Yeah.
Did you understand? And these kind of mathematics would be there, so you have to solve for mu also in rotational spectroscopy also, huh? Then also you remember how to get these things, okay. 17.5 into 1.66 into 10 to the power minus 27, okay, so that would give me 2.91, or suppose 905 into 10 to the power minus 26 kg. Now I will get the new vibrational from here, so that is 1 by 2 pi. It already given that this is 2893.8. I have boiled down it to kg second to the power minus 2, right, Newton per meter 2, and this is 2.905 into 10 to the power minus 26 kg. Now the kg will cut. I'll give you the whole term, okay. What will be the new vibration? So 2893.8 divided by 1.905 divided by 10 to the power minus 26. Okay, so that would give me, and if I took a square root of that would give me 3.89, or suppose 3.90 into 10 to the power 14 by 2 into 3.14 second inverse, or hertz, right, or hertz. What is that is actually going to be divided by 2 divided by 3.14. So I am doing the calculation in my phone, so I can make mistakes, please let me know if I am doing it. 206 into 10 to the power 13 second inverse, okay. Now E0 is half into h is Planck's constant 6.626 into 10 to the power minus 34 into nu bar we know 6.206 into 10 to the power 13 second inverse. And what is the unit of Planck constant, can you tell me? Antika?
Meter square kg per second. Kg meter per second square.
Kg meter per second square. So another term would be joule second, right? So as we are going to use joule as a unit, so it would be same, right? Joule is Newton meter, again Newton is kg meter second minus 2. These are the things. So second will cut and you will get only joule, and the thing is going to be divided by 2. This will give you something around, I think I have made a mistake somewhere. The answer I am getting is a little bit different. 229. Acha, I have done the mistakes here. I have chosen 2293 instead of I have chosen 2 instead of 2293 I have chosen 289. I'll do that again. 2293.8 divided by 2.905 divided by 10 to the power minus 26. That will give me this. Square root of that will give me this divided by 4. So I'll just erase this part. Okay. Let me erase this part. Okay, so I will get something around 4.4745. Okay, 4.4745 into 6.626 into 10 to the power minus 30 divided by. Now I got the answer. That is 14.8 into 10 to the power minus 21. Okay, so this you will get as your answer. So in future, can you solve the problem like this? So the main trick was to get the mu in to the kg, right? The rest of the part is just a calculation. So did you solve this kind of problem earlier, or you were seeing this problem for the first time? Means at least changing the mu from gram to gram per mole, or so this is also known as, so don't when it is given in AMU, that is atomic mass unit, or small AMU, or in daltons. Okay, these are all same. Okay, gram per mole is same as AMU, same as dalton. Okay, so the main trick was here. Okay, so I hope you could solve this problem again. So the main thing is the unit, so play with the unit. And what about question number 8? Says the wave function for a harmonic oscillator that described by nx exponential minus ax square by 2 has. So what do you know what does this, only this part of a, what this looks like, exponential minus ax square by 2? Don't have to think about a. Exponential minus x square by 2, how does it look like? It's a very common distribution. You have, I am sure you have heard it somewhere. So have you heard something Gaussian distribution or the normal distribution?
Yeah, Gaussian distribution. Yeah.
Yes, this is actually from the Gaussian distribution. Now when you multiply with the x, so this would, so what is the Gaussian distribution actually looks like this. It falls off very quickly, both the sides. It is almost, suppose there is nothing a, it would be x is equal to 0, it would go very. Now when it is, I think, n into x, n is the, suppose some n is the normalization constant, and x is actually, for a harmonic oscillator you get something in terms of x or xi, that is Hermite polynomial. So that is actually some polynomial of x. Okay, so here it is given x. Okay, so x exponential minus, so for this what do you expect? Suppose this is my x is equal to 0. what do you expect the graph should look like? Avantika, did you have mathematics background in your 12th, 11th, 12th, and in your BSc?
Mm, no.
Okay, so you are from which background? Means in BSc you have studied chemistry.
Yeah, I have studied chemistry, but not mathematics. I had zoology and botany with sorry, chemistry.
Okay, during your BSc.
Yeah, even with in 11th and 12th.
So which board do you belong to? Which may I know?
JNK board.
Which?
JNK board. JK
JNK board.
board.
Acha, you are from JNK. Okay, okay. So I have one of my friend Shivalika Sharma. She is also from JNK. She is in my batch PhD. Whatever else. Acha, you are also Sharma. Shivalika Sharma. Do you know her? Shivalika Sharma. Just asking out of curiosity.
Shivalika Sharma.
Yes, studying in doing PhD at IIT Bombay.
No, I don't.
Anyway, so let us not digress. Okay. So do you know how this equation would look like, or how the graph would look like?
No,
Okay.
actually, I also got this question wrong.
Okay. So what did you write? So what option did you choose?
Then I didn't know the answer, so I just picked randomly.
Hmm?
I didn't know the answer, so I just picked one randomly. So
Okay. So actually, if you check the graphing calculators also, or it will actually look, so from at infinity it is 0. It will be high here, and then it will pass. It will have a minima. Then it will pass through x, and it will have a maxima. So do you know what is a minima and what is a maxima?
yeah,
This actually not to the graph, not to the scale, but so what here? What is a which one is a minima and which one is a maxima?
the maximum, the highest position on the graph, the one on the positive axis.
Yes, yes.
Positive plus right.
So this is the maximum and this is the minimum. So do you know how to calculate maxima or minima from a equation? We have done that, right? For the population of a rotational spectra, suppose that population was given by, I think, P was given by 2j plus 1 exponential BAC A plus 1 by. This is the population of the jth step, right? It is not the ratio. The ratio will come minus delta E, something like that. Please check that part also. Huh? So actually the Boltzmann constant looks like exponential KBT minus delta E by KBT. When there would be a, when there is a difference, else it is E1 and E2. Let us not go to there. Exponential BAC by J1 by KT, right? Something like that we have already done, right? And to get the maximum, for which J max, I mean, so, for which J the population is maximum, that is that, right? You got it, right? What I am trying to say. So dpj by dj you have to do, and you have to get a for which j the derivative is 0, but that doesn't mean that j will give you maxima only. That can give you maxima, sorry, and as well as minimum. Okay. So then you have to do a double derivative and understand, or you can put the values and get if it is you are getting a positive or a negative value. Please look into internet for this kind of problem. Okay. So for this question, what you are getting, one maximum and one minimum only. Okay. So, and so this is a maximum, this is a minimum. So what do you think about this graph? Suppose this will go through this and this and this. So what do you expect? How many? So this is the maximum. Okay, this is maximum. But these are also maximas, and this is also a maxima. Means the maximum is always a maxima, but you understand the delta pj by del j or something like that. That means here the slope is 0. So for this minimum also or minima also you will get the slope 0, change in the thing. Okay. So today we'll wrap it up here. Okay. So because there is some interview of my senior is going to take place. So today I will wrap it up here, and I hope you have understand the things what we have taught here, and we'll discuss the week 4 in details. Did you read the week 4 and did you have any doubts? Do you have any doubt?
Yeah, I've read the week 4, just last video is remaining.
Okay. So please read that part also and solve the assignment 4. We'll discuss that perturbation theory in details in the next class. What sir is doing. Huh? I know the perturbation theory and the quantum mechanics could be a difficult thing. That is difficult for me too, but we'll try to do that together. Okay then. So today we'll stop it here, and I will share these files for the future reference. And okay.
Okay, sir.
Oh, again you are telling me sad. I am not sad.
Sorry.
It's okay. 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 Bye then. Meet on the next class.